Okay, so far we've mostly only discussed acids, even though this chapter is titled Acids and Bases. So let's talk a little bit about the latter. The good news here is that the types of equilibria and assumptions we make to solve these problems are quite similar. In general, the Bronsted definition of a base in aqueous solution, a generic base B, is a substance that can accept a proton from water, forming B's conjugate acid, BH+, and hydroxide ions, which are the conjugate base of water. The latter is what causes the solution to be basic, particularly as measured by the pH scale. Our base dissociation constant, Kb, looks pretty similar to the Ka expression for acid dissociation. We have our base concentration on the bottom, and the conjugate acid and hydroxide concentrations multiplied together on top of the expression. For instance, using probably the most common example of a weak base, the dissociation of ammonia looks like this. Because ammonia can accept a proton from water in an equilibrium reaction, we get the ammonium ion, its conjugate acid, and hydroxide ions present in solution, and hence the Kb expression has the ammonium and hydroxide concentrations multiplied together, divided by the ammonia concentration itself. Just like Ka values, Kb values are known for many weak bases, and would largely be provided for you as needed. You can also see the Ka values for each of these bases' conjugate acids. More on how those two are related in just a few moments. Let's put some numbers to one of these weak base equilibria. Let's calculate the pH of a 0.40 molar ammonia solution, for which Kb is 1.8 times 10 to the minus 5th power. Building a nice chart, we can see that the initial concentration of ammonia is 0.40 molar, the initial concentration of its conjugate acid is 0, and the initial concentration of hydroxide ions, which is technically 1.0 times 10 to the minus 7 in pure water, is essentially 0 for our purposes. Taking into account the decrease in ammonia concentration and increase in ammonium and hydroxide concentrations as a result of the partial dissociation, we have our expressions for the concentrations of each substance at equilibrium, and the same Kb expression for this dissociation that we saw previously. If we plug in the Kb value, 1.8 times 10 to the minus 5, and the expressions for the equilibrium concentrations, and assume that 0.40 minus x is essentially just 0.40, we get an x value of 0.0027 molar. Now, an important thing to remember with these weak base equilibria is what x represents. Specifically, our hydroxide concentration is equal to x at equilibrium. This is related to, but not the same as, the hydronium concentration that we calculated in our weak acid problems. So it's important to find the relationship between these two to calculate hydronium concentration to find the pH. Hydronium concentration is 1.0 times 10 to the minus 14, or Kw, divided by hydroxide concentration, the 0.0027 molar from before. This gives us 3.7 times 10 to the minus 12 molar. Now we can calculate the pH by taking the negative log of this hydronium concentration, which gives us 11.43. A good way to make sure you aren't missing something is to keep in mind the context of this problem. We're trying to find the pH of a weak base, so your answer should be larger than 7. If it isn't, you likely forgot to convert the hydroxide concentration to hydronium concentration, or possibly converted it incorrectly. Now that we've considered Kb, let's talk about an important property of these equilibrium constants we've discussed. The first equation here shows the dissociation of the ammonium ion, which, being the conjugate acid of a weak base, is itself a weak acid. So this equilibrium corresponds to the Ka for ammonium ions. The second equation is our dissociation of ammonia from the previous problem, which of course corresponds to the Kb for this substance. Now an interesting thing happens if we add these equations together. The conjugate acid-base pairs cancel out, and we end up with the dissociation of water into hydroxide and hydronium ions. And of course, this is the dissociation that corresponds to Kw, as we saw before, and Kw has the constant value of 1.0 times 10 to the minus 14. This is significant because if we know either the Ka or Kb value for a weak acid or weak base, respectively, we can always determine the other value for its conjugate base or conjugate acid. And sure enough, the Ka value for ammonium, 5.6 times 10 to the minus 10, multiplied by Kb for ammonia, 1.8 times 10 to the minus 5, is in fact equal to 1.0 times 10 to the minus 14. This illustrates an important general property. For any conjugate acid-base pair, the Ka of the conjugate acid and the Kb for the conjugate base are related by the equation Ka times Kb always equals Kw, or 1.0 times 10 to the minus 14th power. A related equation, which combines this relationship with properties of logarithms, is that pKa, the negative log of Ka, plus pKb, the negative log of Kb of the conjugate base, always add together to pKw, the negative log of Kw, which is just 14.00. Now that we've discussed both acids and bases, let's talk about the acid-base properties of salts. Many salts, or ionic compounds, produce aqueous solutions that are either acidic or basic. First, let's consider the ions found in common salts that don't appreciably affect the pH. These are the cations from strong bases, so alkali metal cations, as well as alkaline earth metal cations other than beryllium. Likewise, the anions from strong monoprotic acids also do not appreciably affect the pH. So chloride, bromide, iodide, nitrate, and perchlorate all do not affect the pH, since they are the conjugate bases of strong acids. Let's consider an example salt, ammonium chloride, NH4Cl. We'll consider each ion, ammonium ions and chloride ions, separately, and then combine the results. The ammonium ion, as we saw previously, is the conjugate acid of a weak base, and hence is itself a weak acid. So ammonium ions on their own will tend to produce a weakly acidic solution. And then we saw in the previous slide, chloride ions don't affect the pH either way, so the net result is a weakly acidic solution. We saw that alkali metal cations and most alkaline earth metal cations don't affect the pH in water, but how about other metal cations? The answer is that, in aqueous solution, most metal cations other than those just mentioned have a tendency to create weakly acidic solutions. This is especially true for cations that are smaller and/or have higher positive charges. To illustrate this, let's consider hydrated aluminum ions in solution, where each aluminum 3+ ion is bonded to 6 water molecules in octahedral molecular geometry. Due to the strong positive charge of the aluminum ion, the electrons in the water molecules are partially attracted to the central aluminum ion. This has the net result of weakening each hydrogen-oxygen bond. Due to the weakened bonds, it's easier for these water molecules bonded to aluminum to donate a proton to other water molecules in solution. This equilibrium dissociation produces some hydronium ions in solution, and hence produces an acidic solution overall. Because smaller and/or more highly positively charged metal ions will have stronger effects on their bound water molecules, the acidity of solutions containing metal cations will increase as the charge on these metal ions increases, or for ions of equal charges, the effect will be stronger for ions with smaller radii. Let's consider another possibility, weakly basic salts. For instance, a salt like sodium cyanide contains sodium ions, which as we saw previously won't affect the pH. So how about the cyanide ions? The conjugate acid of cyanide is hydrocyanic acid, HCN. Since this is a weak acid, we know that cyanide ions, being the corresponding conjugate base, are weakly basic themselves. Since the sodium ions don't cause an effect on the pH and the cyanide ions are weakly basic, the overall effect is that a solution of sodium cyanide will be weakly basic. If you followed all the previous sections, it's not too difficult to predict whether a salt will be acidic or basic if only one of the ions has acidic or basic tendencies and the other doesn't affect the pH. But what about the salts with both acidic and basic ions? Let's consider ammonium carbonate. We've seen before that ammonium ions are weakly basic, as illustrated by the first equation here. Likewise, carbonate ions are weakly basic, since their conjugate base, bicarbonate ions, HCO3-, are only very weakly acidic. When we encounter a situation like this, there will be one of 3 possibilities, and the result is fairly intuitive. If the Ka of the weakly acidic ion is larger than the Kb of the weakly basic ion, the solution will contain an excess of hydronium ions and the pH will be less than 7. In brief, if the acidic ion is more acidic than the basic ion is basic, the solution itself will be acidic. In the opposite case, where the Kb for the basic ion is larger than the Ka for the acidic ion, the solution contains an excess of hydroxide and will have a pH higher than 7. In other words, if the basic ion is more strongly basic than the acidic ion is acidic, the solution will be basic. And finally, if the Ka and Kb values are equal, or at least approximately equal, we'll have a similar concentration of hydronium and hydroxide ions. In other words, we'll have a neutral solution or a very nearly neutral solution. So getting back to ammonium carbonate specifically, we can calculate the Ka for ammonium ions and the Kb for carbonate ions. These might be provided for you outright, or we can calculate them from each ion's conjugate acid or base. In this case, the Ka for ammonium is 5.6 times 10 to the minus 10, and the Kb for carbonate ions is 1.8 times 10 to the minus 4. Since the Kb value is much larger, more than 100,000 times larger, a solution of ammonium carbonate will be basic overall. This chart summarizes all the possible combinations of ions and the net result of a salt on the solution's pH. There isn't much to say here that wouldn't just be repeating what I just said, so let's wrap things up by moving on to Lewis acids and bases. Very briefly, we're going to look at a definition of acids and bases that differs from the Arrhenius definition from first semester general chemistry, or the Bronsted definition we've been going over in this chapter so far. Lewis acids and bases are defined not in terms of proton transfer, but rather in terms of donating or accepting pairs of electrons in chemical reactions. A Lewis acid is an electron pair acceptor, while a Lewis base is an electron pair donor. A simple example would be the protonation of ammonia. Under the Bronsted definition, H+ is a proton donor and ammonia, a weak base, is a proton acceptor. However, if we shift our focus to how the base-proton bond forms, we'll see an example of a Lewis acid-base reaction as well. The NH single bond that forms when ammonia accepts a proton results from the lone pair of electrons on the nitrogen in ammonia transforming into a bonding pair of electrons between the nitrogen and the new hydrogen. Because the ammonia molecule provided the pair of electrons needed to form the bond, ammonia is considered a Lewis base, or electron pair donor, and the H+ ion accepted this pair of electrons to join in forming a single bond, so it's considered a Lewis acid. We can extend the notion of Lewis acids and bases beyond reactions involving the types of acids and bases we've seen before, though. Common examples of Lewis acid-Lewis base reactions are the formation of so-called complex ions between a metal cation and some sort of electron donor. For instance, copper 2+ ions in aqueous solution, being positively charged, are capable of accepting pairs of electrons to form bonds. Ammonia, as shown in the previous slide, is an electron pair donor, and is capable of providing the electrons needed for such a bond-forming reaction. In particular, copper 2+ ions are capable of accepting electron pairs from 4 ammonia molecules to form the complex ion shown as the product of this reaction here. Since Cu2+ accepts these electron pairs, it is a Lewis acid. Likewise, since the ammonia molecules donate the electron pairs to form the bonds, they are Lewis bases. Like many reactions that form complex ions, this reaction can be monitored by a very nice color change. Copper 2+ ions in aqueous solution are a nice light blue color, while the product complex ion produced by this Lewis acid-base reaction impart an equally nice deep blue color to the solution. You'll see a similar color-changing reaction when you perform the potassium ferrioxalate lab in person in the coming weeks, which is another complex ion formation reaction resulting from the combination of Lewis acidic Fe3+ ions with Lewis basic oxalate ions. And with that, we can bring Chapter 16 to a close. I realize this was a very information-dense series of videos, so thank you for your attention if you've made it this far, and please continue to stay safe out there.